Hi everybody. Today I'm presenting our paper TUM Autonomous Motorsport, an autonomous racing software for the Indy Autonomous Challenge. What you will see in this video is the result of over 3 years of research by the Technical University of Munich. When we talk about autonomous racing, we ask the question, is this the future of racing? When you look at racing vehicles right now, you see that number one, as a race car driver, you need to detect the vehicle limits. You drive in an unstructured environment where you have a different track and condition. Number two, you make decisions at the vehicle limits. You have this high prediction uncertainty, you need to overtake at high speeds, and you need to take care of your strategy and energy constraints. Ultimately, in number three, you see the handling at the vehicle limits. You have high speeds, high accelerations, and high planning horizons with only small reaction times. When you combine all these three parts together, you will have a very exciting topic if you want to make everything you see here completely autonomously. And that was the idea of the Indy Autonomous Challenge. In the Indy Autonomous Challenge, we had multiple challenges. First, we had the Indy Autonomous Challenge at Indianapolis, where we had a single vehicle competition, and the qualification defined the seeding. Ultimately, we had a fastest lap competition and an average speed of 4 laps. Then, number two, we had the Las Vegas Autonomous Challenge. This was a multi-vehicle competition where the qualification defines the seeding and cars need to overtake each other. The speed is increased after each overtake and the last car overtaking wins. What was given to us is the so-called Dallara AV21. What you see here is a full autonomous race car. This is an Indy Lights vehicle chassis with a combustion engine and a 6-gear transmission. Additionally, it was retrofitted to be an autonomous vehicle with GPS, radar, LiDAR, and camera, and of course, a high-performance computer. This was our car that was used by us to then provide the main contribution of this paper to develop the software architecture. In this paper, we present our complete new software architecture for autonomous racing. This software architecture is split into different parts. First, we have an access to the sensors like LiDAR, camera, and radar. Second, we do a localization. Third, we do object detection. Then, number four, we have a prediction algorithm, object checking and prediction. And then we come to the heart of our software, the planning algorithm. Ultimately, we need to control the vehicle to have a safe path and velocity controller. This is the software architecture we presented in the paper and is the main architecture behind our software stack. What we will do now, we will go into detail of each of these fields and I explain a little bit more in detail what's going on here. First is the localization part. We are relying heavily on a multi-sensor fusion. We are using GPS information, we are using IMU information, we are using LiDAR information and the track layout information. These 4 multi-sensor data is used then in a Kalman filter to optimally get the accurate position. What we need here in an autonomous race car is an accuracy of about 2 centimeters to drive optimally on the racetrack. If one of the sensors is dropping out, we have the access to the other sensors and then can use that information to localize ourselves. Number two, the object detection. Here we are relying heavily on a late fusion and tracking algorithm, but we will use the whole information of the sensor setup. We are using LiDAR in a point RCNN, we are using radar with an object list, and we are using the camera object detection based on YOLO. What we will do here then, fuse everything together in a transformation, a plausibility check, an object matching, a state estimation, a delay compensation, and then have a unified object list. What you see here in this example is our point RCNN and the detection on the racetrack of other objects. When we have the know-how of the other objects, it's time for us to have a prediction. We are using various algorithms. For example, what you can see here, our online watch and learn it approach, where we can predict the motion and the behavior of other vehicles precisely. We can get the observations during inference and then overfit to a specific behavior. Therefore, what you can see on the right side is that we get an accurate vehicle prediction for other objects. Ultimately, everything is coming to the planning algorithm. What we are doing in our race car is that we split into a global planning and a local planning approach. In the global planning, we have different optimization approaches, but heavily rely on optimal control, where we're setting up a nonlinear problem optimization with a double track model. By having wheel-specific wheel knowledge, we can calculate the optimal minimum time that the car needs around the racetrack by taking care of exact vehicle behavior from a double track model and the exact friction coefficient. What you see here on the right side is the minimum time in green for one racetrack, which is definitely better than the minimum curvature or the shortest path optimization. Then we go into local planning. What we do here is split the local planning into a sampling-based graph search in a local search and then to an additional local re-optimization with MPC. First, we have a local graph search approach. In this approach, we create a graph over the whole racetrack and then search online for the optimal path and the optimal velocity. This planner allowed us to reach a velocity of 273 kilometers an hour and a very big acceleration of over 22.5 meters per second squared. With this approach, we allow for dynamic overtaking maneuvers at the limits and for high-speed maneuvers. Finally, when we have the path planned, we go into the controller. We are using here a so-called tube MPC approach. The tube MPC allows us to figure out no constraint violation and have a fast computation of the model because we are only using point mass model here. What you can see here on the right side is that our pre-planned trajectory is refined with the MPC. We can take care of uncertainties via low-level control, and we are capable of running at around 100 Hertz in this tube MPC. Ultimately, everything is then brought into simulation and on the real vehicle. What you see here is that we drive on the left side in simulation and on the right side on the real vehicle. We learn from simulation for the real vehicle and we learn from the real vehicle in simulation. When we're done in simulation, it was time for us to test on the real vehicle. What you can see in this video here is the first test of our car in an overtaking maneuver in a controlled environment. What you see here is an overtaking maneuver of our blue car against one of our opponents. You can see here the whole surface I just explained is running on the car. The goal of this competition was to drive on a real racetrack. What you see in this video is one of the final rounds of our Las Vegas Indy Autonomous Challenges event. You see here the two cars driving over 200 kilometers an hour and doing overtaking maneuver constantly. Everything you see here is completely autonomously. Everything you see here is driving at the handling of limits. Everything I just explained is written down in the paper as it's detailed. Please reach out to me if you have any questions. What we will then do as a final part of this project is to provide some open challenges for future researchers. Right now, the vehicle dynamic knowledge and the road friction estimation is a very difficult part. Only with that kind of knowledge, you are able to drive at the handling of limits. Then we need to control the car beyond and at the limits. Ultimately, we need some real-time capable code. Just because you have a cool algorithm doesn't mean that you can run this algorithm fast and reliably. Then the sim to real gap is still an open problem and of course working with real hardware. Ultimately, we figured out that when we compare ourselves to F1 drivers, we have still a lot to learn because F1 drivers learned to race and race started racing many years ago. They started in lower classes and stepped up in racing year by year. Ultimately, these are guys that have many years of experience and a 1,000-man company behind them. Therefore, we still have improvement to beat the F1 driver. I'm saying thank you very much for listening on behalf of the TUM Autonomous Motorsport team. If you have questions, please feel free to reach out to us.